Thanks for inviting me. My name is Semih Salihoglu. I'm a professor at University of Waterloo. I am a database researcher. That's my group. We work on database management systems, and I know this is an AI event, and I'll try to connect this project that I have that I'm here to talk about also with AI at the end. So I've got three goals with my presentation. So I'm going to be talking to you about a new graph database management system that we're developing in my group called Kùzu. So part of the presentation is kind of educational. I want to kind of tell you a little bit about graphs. Why would you want to model your data as a graph instead of tables, which is the standard data model in database management systems? And what are graph database management systems? When should you want to use it, or when do people need it? Then I'll tell you a little bit about Kùzu's vision as a system, and then in the last part, I'll connect it with AI and tell you about an application of training large graph neural networks with Kùzu. So before I start, I just want to kind of get a feeling for who has heard of Neo4j, graph database management systems. Okay, a good number. So it's not a very unfamiliar concept, but I'll still sort of start with basics just to set this stage. Right. So let me start with this question. So what are graphs, or another term for graphs are networks? They are essentially, the right way to think about them they are out of the two possible data models or data abstractions to model your records. They're one of the two of the generic natural ones. So the first one is what everybody is familiar with, tables or relations. The second one is graphs. So throughout history of database management systems, systems have either been really modeled on tabular data model or a graph, some version of a graph. And graph is a little higher level than tables. You are closer to, if you're familiar, to the entity relationship model. It's a bit more object-oriented. So you make a distinction between sets of records that represent entities and sets of records that represent connections between entities, right? And when you plot sort of these graphs that are really complex, you get these pretty things. It's not very useful, but that's kind of the network figure that you might have in your mind. Right, so to compare and kind of motivate why would you want to use a graph database management systems or model your record as graphs. So let me just sort of set the stage by reviewing the relational database management systems and core components of these systems. So as a data model, when you use a relational database management systems like Postgres, you model your records as a set of structured tables. There's very rigid. You kind of say very explicitly, here are my records, here are my tables, here are the columns. And you will use SQL as sort of the de facto high-level query language over relations. And then, there's sort of different classes of systems that implement SQL. And, roughly, sort of a bird's overview sort of view of the market, there's tons of relational systems, but you could think of them as columnar systems and transactional systems. Columnar systems are the ones you would use if you have read-heavy workloads, analytical workloads, and OLTP or transactional systems is if you've got a lot of transactions that you want to enter in a safe way, right? So how should you think of graph database management system in this context? And I don't want to sort of tell you that you should not use relational systems. That's not the message that I'm going to give. You should certainly, if you've got very sort of fixed sets of records that you can structure as a set of tables, and your workloads are such that you can use a relational systems, that's the first go-to database management systems for any application developer. Okay, so you should try to use relational systems. But there are many cases, as I will show you, where the relational systems are not going to be sort of good for you. It's not going to be natural to model your data, or they won't give you the performance that you would need. And those are the cases. That's the kind of message that I'm going to try to give you. So that's why I gave you the relational systems overview. So I'm just going to sort of compare what graph database management systems look like, right? So how should you think of them? So you should think of them as read-optimized systems. So don't think of them as like transactional systems that are really designed to take thousands of or millions of transactions per second. They're not designed for that. They're read-optimized systems. They've got very good capabilities to do certain read-optimized operations. They offer a graph-based model in essentially comparison to relational models. So you specifically say, here are my nodes, node records, and here are my relationship records. And you can put key value properties on your nodes or your relationships or your edges. Okay, so in some sense, this is kind of It's very similar to the relational model, right? So, but there is a distinction that you make between your sets of tables, as these are node tables and these are relationship tables. Okay, that's another way to think of this data model. The query languages are also designed to be SQL-like. They're high level, like SQL-like. And you should really understand what's going on in this sort of standard way you understand SQL as operations that perform joins, filters, group bys, aggregations. Okay, it's actually, these systems like Neo4j or Tiger Graph, their high-level languages are kind of meant to be like SQL, right? And that's not a coincidence, because the only way humans, we engineers, know how to develop high-level query languages is to sort of make it based on these relational operators. So that's how we know how to compile sort of high-level languages into low-level executable code, right? So here, I'm showing you a snippet from the language of Kùzu, which is the language of Neo4j Cypher. It's a sort of, you should think of it as a graph optimized or graph-specific SQL. The joins normally in SQL would be expressed in a from clause. Instead, it's expressed in a match clause. In a match clause in Cypher, and instead of listing a set of tables, you draw a graph pattern. So you're drawing an edge. You're trying to connect or join your A records. That's a variable that you would give to a table, for example, in SQL, through a transfer edge to a B record. Okay, so I'm throughout the talk, I'll be kind of, my running examples will be modeling a financial transaction network. You've got account nodes and then transfer edges, right? So that's the examples that I'm going to be talking through. Where is exactly like SQL's where, and return is corresponds to select, where you do the group bys or projections, right? So this is essentially asking for the names of the name property of every account that Bob has transferred money to. Okay, so it's, you can read it as you would read in English, right? And in terms of the sort of the actual system implementations that implement Cypher, there's always going to be some graph optimized sort of features. Sort of, for example, the storages of these systems, they always have some kind of graph optimized storage. Like if you're familiar with graph optimized formats, something like a CSR or an adjacency list format, they'll index, for example, the neighborhood of every record, and I'll tell you a little bit more about that. And they might have certain operations that you might not see in Postgres or MySQL, something like shortest path, which is a very graph-specific operator in your query plans, right? So I said here that, the features in the system implementations are optimized for graph workloads. Now, that's a colloquial term. That's not a very sort of scientific term. So let me tell you what that means for most people. So that kind of requires a definition. And this is what you should have in your mind if you want to detect, when you look at your workload, whether or not it is a graph workload, right? So one thing is that if you've got an application and you've got some sets of records, and those records and maybe the queries you're going to ask over them require some kind of something, what I'm sort of, again, this is a colloquial term, but something that's a bit more beyond relational. So like, for example, if you care in your application about paths between entities, right? So is this account connected to this other account that's suspicious, for example? Like, those are a lot easier notions to reason as in a graph-specific notion of path, and they don't really have a sort of a corresponding notion in the relational model, right? Or if your data is it's impossible to tabulate, and I'll give you an example of this. Sometimes the model that the application, the sort of the records or the facts that the application is modeling is extremely complex, in which case it's impossible to find a set of tables, sort of rigid tables, to actually model your records. Those are the cases where you need something a bit beyond relational, and you'll want some kind of a graph model. Okay, I'll give you again an example of this. The second one is, this is not really a sort of a limitation of the relational model, but this is kind of a limitation of existing relational systems, that if you got data in which your entities depict many-to-many connections, right? So for example, financial transaction networks, one account transfers to thousands of other accounts, or one person in a social network might be connecting and becoming friends with hundreds of other friends. So if you got these many-to-many sort of relationships, those are also data that's very natural to think of as a graph. Not that you can't model it as a table or as a set of tables, you can, but often when your data depicts many-to-many relationships and you need to maybe find patterns in those many-to-many relationships, the performance that you're going to get from relational systems are going to be horrific. So those are the cases where the system implementations really fail. Not really the modeling capabilities of the relational system, but actual system implementations are inefficient, right? So graph database management systems, that, as I'll tell you, tend to kind of offer several sort of optimizations inside the system to be good at data in which many-to-many relationships are kind of at the core of the data set, okay? So in light of this, so what are some differences between graph database management system and relational database management systems in the kind of system implementations and query languages? So let me give you a bit more concrete sort of differences between these two classes of database management systems. So the first one is the joins. When you join your records, either in a relational system or a graph database management system, that's probably the most core operator, that operation of database management systems, the join records to construct larger and larger records, so you can essentially do much more interesting things than the base records. So the joins, which is the core operator of database management systems, are value-based in relational systems, and they are predefined or pointer-based in graph database management systems. So let me tell you what I mean by pointer-based or predefined joins. And that's a term I'm using intentionally because it was a term used by Ted Code. So for those of you who don't know Ted Code is the inventor of relational systems. He's a Turing Award laureate, so equivalent of the Nobel Prize in computer science. So Ted Code, as the inventor of relational model, was criticizing the, this is actually a quote from his Turing Award lecture. He was criticizing the graph database management system of his era by saying that, look, in the relational model, you could join any two tables on any two columns arbitrarily, as long as those two columns have the same data types. Maybe they're both strings or they're both integers. Okay, so that's a capability that you could do in relational systems. And he was criticizing the graph database management systems of his time by saying, in the graph database management systems, you can only join sort of these node entities with the neighborhood, but the neighborhood needs to be predefined to the system. You predefine to the system that here are the edges of this node, and the system needs to know about this. So he was criticizing them, saying that they're not as flexible as the relational system, right? So nowadays, this distinction is a little bit gone, and let me put you the graph database management system of Ted Code's era, and there was a big fight in the database community back in the day in 70s, 80s between the graph-based models and relational systems. This is Charlie Bachman. I bet very few of you, if any, have heard of this. He's another Turing Award laureate. And he is the inventor of database management systems. He's credited to have invented database management system, to have implemented or led the first database management system in history called IDS. And it was based on a graph-based model. It was actually called the network model, which is just another term for a graph. I'll show you another picture. And to some extent, this distinction of predefined versus value-based joins still exists. Doesn't exist anymore. In graph database management systems like Neo4j or Kùzu, you could join node records arbitrarily with each other. But it actually is an advantage for graph database management systems that on those predefined joins, they can be very fast because the system already knows what it's going to join, right? Because the neighborhoods of those node records have been defined to the system, so they can actually take advantage of it. So almost universally, for example, all graph database management systems are going to have a join index, which no relational system has, right? So that's one difference. And since I'm a professor, I could go a bit more into the sort of the history. And here's a picture from 1962. And you can see the graph, I hope, visibly there. There are sort of these records that are the nodes, and there are these edges, which are other records that connect the nodes. And that's from Charlie Bachman's IDS system. That's is sort of from the design of the first database management system in history. So that has sort of throughout history, graph-based sort of systems have all database management systems have always been built. They've always kind of been predefined or have supported pointer-based joins, right? The second difference, and I'm going to be obviously focusing on the advantages of graph database management system, because the message that I want to give is that these are the times where you might want to use a graph database management system over a relational system, is that they are much better in workloads that require some kind of recursive join. So for example, let's ask this question on my running example. Give me all direct or indirect possible sources of money flow into Alice's account from Canada. this is a snippet of code from Cypher, which is very elegant to express this query. It really reads like the English. There's this specific sort of syntax called clean star to represent direct or indirect joins between two A account record and a B account record, right? With some sort of very obviously easy to read filters. Now, this can be done in SQL, but it's harder. It's objectively harder. Let me give you even a more obvious example. So in suppose your computation is, and I didn't give the English version, but to find the shortest sort of paths between one account and another account. Right? Now that shortest path computation is also a recursive join, right? It could be arbitrary length. That's again doable in SQL, but very, very much harder even than the previous query. So those are the cases where sort of SQL or relational systems don't provide the necessary features, right? Now that's again, there's very good reasons for this. When SQL was designed, the first 20 years of SQL had no recursion. Recursion was an afterthought in SQL, and every afterthought that tried to get into SQL has not been very successful. It exists. You could do recursive computation in SQL, but they're just objectively harder, and graph databases are objectively much more elegant to these computations. Again, so as I said, they give better support for many-to-many joins. So here's an example, and this is a feature that I'm going to kind of highlight very quickly from Kùzu. So this is a query that's asking for all two paths where the middle node is an account owned by Liz, and we're asking for the IDs of the source and the destination accounts. So this is this is your input graph, input network. In that network, suppose those L1 and L2 are the accounts owned by Liz. Each of those accounts has 100 incoming edges and 100 outgoing edges. So in the sense, you're doing essentially a two-path, so kind of two joins of 100 records with other 100 records, and there's twice of these. So there's basically 20,000 output tuples for that query, right? So in a traditional system, say Postgres, the system would need to be essentially enumerating all that search space, right? So this kind of explosion in this many-to-many joins is something that in some way hurts the performance of these systems. Whereas in Kùzu, for example, we have specialized query processing techniques to compress such growing joins. So for example, we would represent that same output of that same join by exploiting the fact that those incoming edges to L1 and outgoing edges to L1 actually form a Cartesian product. So they're kind of conditionally independent once L1 is fixed. So you could represent exactly the same 20,000 tuples with only 400 values as follows. The first 10,000 tuples are L1, Cartesian product with 100 incoming edges, Cartesian product with 100 outgoing edges, and similarly for the second 10,000 records. Okay, so graph database management systems, and certainly Kùzu implements several of these features to be a lot more performant on many-to-many joins. And the last one, which I said I was going to give you an example of, are data sets that are just impossible to tabulate. So for example, this is a set of records from the structured version of Wikipedia called DBpedia, right? So these are essentially, the way you should interpret these is that these are records that say in a structured way that Justin Trudeau, for example, has a birth date of this and has a birthplace of Ottawa, which is in Ontario, things like that, all represented as a set of what we call RDF triples or triples. And, the data that's represented in this DBpedia, which is the structured version of Wikipedia, sure, indeed it's structured, but it doesn't mean it's easy to tabulate because, it models something unbelievably complex. It models all human encyclopedic knowledge. What are the tables of that knowledge? It's impossible. So you need something a lot more flexible to represent and structure that data. So, graph-based models are a lot better when the set of records that you're modeling are impossible to tabulate. Okay, so this is a graph representation of the same set of models, and this is another case that if what you're trying to model is hard to tabulate, you are kind of destined to use a graph-based model. Okay, so that was kind of the background on what graph database management systems are, and when I think developers should resort to a graph database management system, pick it over relational systems, and that's basically kind of the main message that I wanted to give in the first part. The other parts are going to be a lot quicker, so I'll be within time. So let me just tell you kind of the vision of Kùzu as a system. So the first obvious immediate goal of Kùzu, the system that we're building, is to perfect this previous feature set that I mentioned. These are the cases you'd want to use a graph database management system and do it with sort of state-of-the-art query processing and storage techniques for graphs. So we want it to be very highly scalable and very fast, and it does perform a lot faster than existing commercial systems. And in terms of its usage, if you have been following sort of the database industry, one of the most exciting sort of systems that came out in the last 3-4 years is DuckDB. That also came from an academic group in Netherlands. Actually close colleagues of mine. So it's meant to be like DuckDB, and I'll tell you a little bit about what that means in terms of its uses. So DuckDB is like SQLite, so it's an embeddable system. It runs as part of your application. It's not a server-client architecture. And Kùzu aims to be like DuckDB, but for graph structured data. And it's open sourced under MIT license. It's got a good engineering team behind it, so it's not being developed as an academic prototype. It's meant to be like Postgres or DuckDB, something that ends up becoming usable in production, right? So we implement the graph data model that I showed you in my initial slides and Neo4j's language cipher. And when I say like DuckDB-like, sort of it's very easy to install. So if you currently on your laptops, if you type pip install Kùzu, you can start creating a database, inserting records, and querying over those records, and it supports transactions. So it comes with the default properties or features of any database management system. And one application domain that we are particularly targeting, which is how kind of this talk kind of relates to this AI event, is we want it to be the sort of the main database or the storage engine, storage system that anybody who's developing a graph analytics or graph machine learning pipeline to use. So we want, if you've got records that you want to model as a graph and you're going to develop a graph machine learning pipeline, or you're going to do some graph analytics over it, we'd like Kùzu to be your main storage so that you get the benefits of these high-level query languages to do your cleaning, transformations, and we want to essentially be able to take your records from any format, even they may come from relational systems. Actually, a lot of the graphs are embedded in current relational stores. Model them as a set of nodes and edges in Kùzu, and then depending on the pipeline that you have, you might sort of get your data out into some graph analytics tools like NetworkX. You know, those are the tools that you would use, for example, if you're doing some kind of batch graph analytics, like find me the cliques of nodes in my graph, find me the communities of tightly knit sort of nodes, or find me my important nodes. So things like rank my nodes according to some kind of notion of importance. So a popular algorithm there is PageRank, for example. Or you could be developing some graph machine learning application. And again, you would want we have integrations to these graph machine learning libraries in the Python ecosystem to make sort of to offer value to people developing these pipelines, and I'll tell you a little more about those. Or even if you're not doing something graph specific, but doing general data science, but your data happens to be much more naturally modeled as a graph, again, we'd like to be the go-to system in the open source to use. Right? So I'll give you an example of an application in the last part of my presentation. So let me tell you a little bit about graph machine learning and graph neural networks and how people use them. So the goal of graph machine learning, again, is a blazingly fast sort of overview, obviously due to time, is to when you have a data that's naturally modeled as a graph that you want to that you represent as a graph, you've got your essentially distinct entities or nodes and relationships, and they might be coming with maybe some feature vectors that define some properties of these nodes. The goal of machine learning, graph machine learning, is basically to just run some computation on this graph and the feature vectors so you can embed them into a vector space. And once they're now vectors and there's no graphs anymore, you're just in the realm of traditional machine learning. So you could do any of the graph sort of machine learning tools to essentially do something predictive in that space. Okay, so this is the main goal. The key idea behind graph neural networks is, it's a specific type of sort of embedding technique, it's a deep learning technique where you want to generate these embeddings in that vector space by essentially integrating features from the for when you're embedding a particular node, you want to integrate features of neighbors and neighbors of neighbors, depending on how many deep layers that you would like to go to, right? So you get essentially these machine learning, deep learning models that are designed where the sort of the architecture of the model is defined based on the neighborhoods of the nodes. Okay, so that's how graph neural networks at a high level embed nodes into a vector space, right? So this feature that I'm going to show you is essentially just to demonstrate how a graph database management system, which is not an AI tool by itself, it's a database management software, it's a storage software with a high-level query language, how could it offer value to people building pipelines around this? So one sort of feature, and this is only one that I'm kind of highlighting, is the graph machine learning, essentially pipelines. One problem that they have is that in particular, there's two libraries that people use. One is PyTorch geometric, the other is deep graph, DGL, deep graph learning library, deep graph learning. And they're both implemented in Python. And one problem that they have is that they have their in-memory storage of graph and the features. Okay, so basically, if you're using these libraries, you're bound to essentially put all your data into the RAM of your CPU. Okay, so when you're using PyTorch geometric, for example, you put your graph topology into PyTorch geometric, you put your node features into PyTorch geometric, which is a lot larger than GPU, and then you will do these mini batches to the GPU to do the training, okay? So this works great when your data fits into your CPU, but you cannot train models that are larger than the CPU's memory, okay? So that's a scalability problem, okay? It's widely recognized. There's tons of papers around this, tons of essentially sort of features people are trying to use. So one feature that we have is that you could use Kùzu to replace PyG's default storage, and that's called, in PyG's terminology, a remote backend. So Kùzu can replace PyG's storage to become the remote backend, where because it's a database management system, as every database management system, we persist our data on disk. So database management systems are disk-based systems. So the way that the flow works is that you're no longer bound by the CPU's memory. You could store data that are much larger than CPU's memory because data is persisted on disk, and your mini batches are generated from Kùzu. First, that go to the CPU, from CPU to the GPU. Okay, so the way you do this is you import PyTorch geometric and Kùzu in your Python code. You create your nodes, you create your relationships. So this is an example of papers and citations. Then you load your data into and features. So features are, I'm assuming, stored in some NumPy files. So you load those node features into Kùzu, and then your graph topology, which I assume is in this edges.csv file. And then the rest is basically you have one call to Kùzu where you say, get me the remote backend for PyTorch geometric. So that gives you a feature store and graph store, and the rest is just your existing PyTorch geometric code, where you just replace the default feature storage and graph storage with Kùzu's feature storage and graph store, and now everything will just work out of disk. Okay, so what can you expect? Obviously, because you're hitting the disk, your throughput is going to slow. You're no longer data is being read directly from memory, but the performance degradation isn't terrible. Okay, so here's a case where this is a data set that requires 110 gigabyte of memory, and I'm showing you sort of how we decrease Kùzu, the amount of memory that Kùzu uses, from 100 to 60, and this is the degradation. So you degrade from 0.28 to 0.38, so on and so forth, but up to like around 4 to 4.5x is when the performance degradation essentially stops. Okay, but in return, you're getting the ability to be able to train on much larger graphs, right? So that's an example of kind of the applications that we're targeting within the graph data science space, graph machine learning space, and those are the kind of values that a graph database management could give you if you are an AI developer or a machine learning developer in the graph space, right? So try it out. it works. Give us a star on GitHub. It's meant to be completely open source. We're committed to keeping it on MIT license. Hopefully throughout eternity as long as the system lives, but it's meant to be like, again, Postgres, or it's meant to be like DuckDB. So we are committed to be developing it for the foreseeable future. So with that, here's a couple links that you might follow just to read a little bit more about the vision of the system, the current roadmaps that we have on GitHub, so on and so forth. Okay, so thanks very much for listening. And I also took a bit more time, but maybe I'll take one question, or I'll take one question and then I'll delay it. So I mean, maybe say a little bit more about what kind of relationships do you have? Like, I'm not sure of what kind of relationships sort of you have in mind. So any sort of set of records that you want to model as a relationship, you can model as a relationship. There's no restriction. Of course, yeah. Of course, yeah. No, you could use vector of, so you could store arbitrary properties. There's a lot of data types that we support. One thing that we support natively, just because we want to place ourselves in the graph, ML space is a vector. We call it a fixed list. So you could say, I have essentially on my nodes, I'm going to I have a feature called maybe X, a property X, and it's actually 128 dimensional sort of floating point number. So you could store those both on your edges and both on your nodes. So we do support data, just like any database management system that supports many data types, you could put many data type properties on your nodes or edges. So there's no restriction in that sense. So I mean, matrices are a way to represent the relationships. So you could obviously sort of take a matrix, and for each sort of edge in the matrix, you could add a record to Kùzu. So you effectively get the sort of the same data, right? So you could, but I mean, if your question is like, do we have a specialized sort of way of storing matrices? We store it in a sparse way. Everything is, every sort of graph that we store is stored in kind of adjacency list-based or CSR-based, disk-based. Disk-based versions of CSRs basically is our core storage structure. Okay, all right. I'll take more questions. Sure. Okay.
So federation have different subgraphs coming from different.
No, not natively. So you mean like two?
Yeah, if you have, for example, if you have different hospitals or banks with different subgraphs of clients or patients that are.
So you could, yeah, so you could model them as different nodes and different edges and put them into the same database and query in the same query. So you can do that. So that's fine. That's not really federation. So federation is kind of a more, it's got a different meaning in database literature, at least, that it's distributed and part of your data is on one machine and part of your data is federated in another machine. So we're a single node system. So that's the point that I was saying. So we're a single node system, just like DuckDB is a single node system. But in terms of your modeling capabilities, you could model as complex a graph as you want, as long as you're going to add new nodes and new relationship types to the system. Okay. Yeah. Okay. All right. Thank you. I'll take more questions. Sort of. I don't want to take more time, but I'll take more because I'll stay longer to take more questions. Thank you very much again. Huh?
Cool.
Thank you.
Thanks.
Awesome.